Welcome to today's lesson. In this tutorial, we will use a transformational approach to recognize and graph a function given its equation. So we have already looked at our parent functions, and today we're going to be moving those parent functions around our graph, and that is called graphing by transformations. But before we do that, I'd like to review point-slope form from Algebra 1. Point-slope form was a form that we used to graph a line, and it was y minus y1 equals m times quantity x minus x1. What point-slope form gives us is a point and the slope. The starting point has an x-coordinate of x1 and a y-coordinate of y1. So this is where we would start to graph our line, that ordered pair. And then we would use our slope, which of course is here the m, to graph all of the other points. Graphing by transformations with our parent functions is very similar. Instead of using the m, the x1, and the y1, we're going to be using an a, an h, and a k. But it's the same idea. H and k are going to be just like x1 and y1. That's going to be our new starting point. It's going to give us a point where our graph starts, and then A is going to be very similar to M. A is going to give us all of the other points for that particular parent function. Now that, of course, is going to depend on which parent we're graphing. So if we rewrite our point-slope formula using our A and our H and our K, the linear standard form would be right here. Y minus K equals A times X minus H. In fact, we can use the A, the H, and the K and put them in all of our parent functions, and we'd have all 6 of them. Our absolute value function would look exactly the same thing, except it would be absolute value bars. And our quadratic function would be the exact same thing, except now it's a quantity that's being squared because it's quadratic. Our square root would have a square root symbol. Our cubic would be the quantity cubed, and our cube root would be a cube root symbol. But you can see that A is the same exact spot in all 6 of these formulas. It's basically the thing that's being multiplied to our symbol. You can see that H is always in the same exact spot in all of these formulas. It's over here with the X. And that our K, right now at least, is over here with the Y. And this makes sense because we're going to find that H moves our graph horizontally along the X direction. That's why it's over here with the X. And that the K moves vertically in the Y direction. That's why it's over here with the Y. But you can see all these formulas almost look identical. It's just that we're changing our symbol around. Now I put ors over here because sometimes you'll see it in this AHK form, but sometimes people add the K to the other side. So this would be Y equals A times X minus H and then plus K. And this symbol, if we add the K, we would have A times absolute value of X minus H and then plus K. And then this one, if we add K, we'd have Y equals A times quantity X minus H squared plus K. So we can just add K to the other side of all 6 of these. This would be the square root of X minus H and then plus K. Add K over here, and we've got Y equals A times the quantity X minus H cubed plus K. And one last one, add the K here, and we have Y equals A times the cube root of X minus H plus K. So sometimes you're going to see it in this form where K is hiding over here with the Y. Sometimes it will have been added to the other side and K would always be over here on the other side. It's nice that A, H, and K are always in the same spot no matter what the parent function is, because a, h, and k each do something different to transform our new graph from the original parent function. Let's list what those things are. A affects the output. That's ultimately what A will do. It affects the output. What we're going to do is we're going to multiply our normal, I'm going to put normal in parentheses, or in quotes here, our normal output by A. So what we do with A is we take what our normal outputs are going to be, and that depends on what parent function we're talking about, and we multiply those by whatever A is. Okay, so that's what A is, and we'll look at that. H shifts our graph. And like I already said, H for horizontal. H shifts the graph left and right. If H is positive, then we're shifting to the right. If H is negative, then we're shifting to the left. Now watch out with H. It's always going to be x minus the value of H. So if you see something like x minus 3, then H is 3. But if you see something like x plus 3, then that must have been x minus a negative 3, so therefore h is negative. It's always going to be the opposite of the symbol that you see here. If you see a minus sign, then h is positive. If you see a plus sign, then h is negative. So be careful about that. And finally, k. The only other thing that can happen when we're transforming our graph, this also does a shift. This is a vertical shift, and it shifts down and up. And hopefully it makes sense. If k is positive, we are shifting up. If k is negative, we're shifting down. Also be very careful with k. If your formula is looking like this, where the k is on this side with the y, same sort of thing as with the h. It's always going to be the opposite of the symbol that you see here. But if it's over in this type of form where the k is here, then it's just the number that you see here, because now it's a plus k. So if you see plus 3, then k is 3. If you see minus 3, then k is negative 3. So that's pretty easy for k when it's over like this. Before we start graphing some of our functions today, I'd like to show you a neat thing that was created by somebody for transformations. This was created on Geometer's Sketchpad. There are 4 graphs here. This is the absolute value function, and this is our quadratic function. This down here is actually a natural logarithmic function. We're not going to be looking at that until later in the year. And this is a sine curve. We're actually not going to look at that until a future year of math. So focus your attention on the top 2, our absolute value and our quadratic. Right now, what we're looking at is those 2 graphs where h is equal to 0. That means that h has not shifted us anywhere. But what I can do is click this, and it animates h. And what that does is it clearly shows you that h will affect the graph in a horizontal direction. As h is positive values, it shifts to the right, and as h is negative values, it shifts to the left. So that's kind of neat for what happens with h. All right, let's stop that. I can now look at k. I'm going to shift to the k1. And now we're looking at k equals to 0, so that means that it's still in its natural position. It hasn't shifted up or down. But if I animate k, you're going to see now k will affect the graph by simply shifting it up and down. It shifts up when k is positive, you can see over here, and it shifts down when k is negative. So that's kind of neat. Let's stop that one. And we've got one more. This is the value of a. Now the normal value for a is 1, meaning that you just multiply your normal outputs by 1, so therefore they don't change. So these are the absolute value outputs multiplied by 1, and here the quadratic outputs multiplied by 1. If I animate h, watch what happens now. this is the value that will make your graph shrink and stretch and actually flip upside down. But you notice that the starting point is not affected at all because H and K have not been changed. H and K are still 0. When A is positive, we're still, going upward. When A turns to a negative value, that's what flips the graph upside down. Let me stop it on one of the negative values. Because A is negative 2.84, we're shifting, or excuse me, we're opening downward now for the absolute value and for the quadratic. So that's kind of neat. It changes our outputs. A is a little bit trickier to deal with, so we're going to have to practice that today. But I wanted to show you that animation from Geometer's Sketchpad. Okay, so let's get to our first example. What we're going to do in these is, here are our steps. We're going to first identify the parent function pattern. So identify which of the 6 parent functions we're graphing. Number 2, we're going to find H and K, and we're going to use those as our new starting point. Once we get to our new starting point, we're going to use A to find all the other points of our parent pattern. So here's our first example, example 1. Y equals the quantity x minus 3 cubed plus 1. Well, since I said cubed, that's a dead giveaway that this is a cubic function. And that means that it's going to generally look like our cubic parent function, and there it is. Now we've got A, H, and K, so we should go ahead and find those. A is always the number that's being multiplied to this symbol, and in this case it's a 1, which is our normal value of A. H is always hiding in here with the x. I see x minus 3, and since this is supposed to be x minus h, h must be the 3. Remember, it's always the opposite of this. I see a minus sign, so it must be a positive. And k, in this case, is over here, and I just see a 1, so there it is, it's a 1. So hk is my new starting point, and in this case, hk is 3, 1. What I'm going to do with that is the h will shift me 3 units to the right, and the k is going to shift me 1 unit up. What I like to do is draw a little star right there. That represents my starting point, and that helps me to visualize where I'm now starting. Remember, the usual cubic function, the parent function, starts right here at the origin. Well, this parent function is going to shift 3 units to the right and 1 unit up. Now, here's our starting point. There's nothing else that's changing because a is the value of 1. So I'm just going to graph my cubic pattern from this new starting point, which means the cubic pattern actually is 0, 0. So this is like my new origin. I can fill in my star. And then from my star, I input a 1. That means I go to the right 1 unit, and then I would go up 1 cubed, which is right here. And then I go back to the star, the starting point. Then I'm going to input a 2, which means go 2 to the right. And then I'm going to output 2 cubed, since it's a cubic function, and 2 cubed is 8. 1, 2, 3, 4, 5, 6, 7, 8. And then I go back to the star. If I could input a 3, then I'd be going up 3 cubed, which is 27, but that's obviously going to be too far off my graph, so I'm going to stop. Now I'm going to go and input some negatives. If I input a negative 1, that's like going to the left 1 unit from my star, and negative 1 cubed is negative 1, so I'm going to be going down 1 from there, and then back to the star. Always start at the starting point. Now I'm going to input a negative 2. That's left 2 units. And negative 2 cubed is negative 8. So from there, I'm going to count down 8 units. 1, 2, 3, 4, 5, 6, 7, 8. And that's going to be enough. Again, if I could go negative 3 units to the left, then I would be outputting a negative 27, but that's obviously too low of a number to be going off the graph patch. Here's my nice cubic function. Connect all of these dots in a nice cubic curve. Make sure you put arrowheads on each side, implying that the pattern continues forever. And there you go. This is our cubic function. It's just that it's been shifted from the origin 3 units to the right and 1 unit up because h and k were those numbers. Let's look at example 2. This is y plus 2 equals the cube root of x minus 1. Well, I just said it. The cube root, that's what this parent function was. But this parent function has shifted as well. We have a value of a, Again, that value of a is a 1. It's always the number that's being multiplied to our symbol. And since I don't see a number out here, it must be the regular 1. So there a is 1. H is equal to, again, h is always hiding in here with the x, and it's a 1 in this case. And k is equal to, k is over here with the y this time, so k must be a negative 2. Remember, it's always the opposite of the symbol that we see when it's with the y. Or another way of looking at it is, what does y have to be to make this side of the equation 0? So negative 2 plus 2 makes 0, so that's why the k is negative 2. That also works for the h. What does x have to be to make this thing underneath the cube root 0? 1 minus 1. That's why h is 1. So I'm going to find my new starting point, hk, and hk in this case is 1, negative 2. So I'm going to go to 1, negative 2, and I like to put a little star. Put a little circle or put a little something that makes you know that this is our new starting point. So there's my star. And now, since a is 1, I'm just going to do my normal outputs. The normal outputs for a cube root, I go to the right 1, and the cube root of 1 is 1. So I go over to the right 1 and up 1. I go back to the star. I don't do the cube root of 2 or of 3 or 4 or 5 or 6 or 7, but I will do the cube root of 8 because I know the cube root of 8 is my next perfect cube, and that is 2. That's why I get to go up 2 units. And then back to the star. I'm not going to go all the way over 27 because that's too far off the graph patch. But I will go in the negative direction. The cube root of negative 1 does exist. The cube root of negative 1 is negative 1. So when I go left 1, I will go down 1. Back to the star. The next one I'm going to do is negative 8. So 1, 2, 3, 4, 5, 6, 7, 8 units to the left of the star. And then I get to go 2 units down. And that is our cube root function. Let's connect our dots in a nice smooth curve. Don't get sloppy here. And put arrowheads on each side. That is our cubic function. Sorry, our cube root function. It's just been shifted to the right 1 and down 2. So this is graphing by transformations. We're basically using our parent functions, deciding which pattern we're supposed to be doing, and then finding our new starting point. So let's look at example 3. Y plus 2 equals 1/2 times x minus 3. Well, that's not any fun little symbol. There's no other weird symbol other than the 1 here as an exponent. So this must just be our regular line. This is just linear. This is something we graphed in Algebra 1. A is equal to 1/2 in this case. H is equal to 3. And k is equal to negative 2. So our starting point, hk, is the ordered pair 3, negative 2. So that's where I'm going to start. I'm going to go 3 units to the right and 2 units down and put a little starting point. Now this is just linear, so it's basically a line. It just has a slope. And in this case, our slope is the value of a, 1/2. So a slope of 1/2 from this starting point would be rise up 1 and run to the right 2. And I'm going to do that as many times as I can. Up 1 and right 2, up 1 and right 2. I'm out of a graph patch over here, so I'm going to go backwards. I'm going to go down and left, down and left, down and left. Down 1, left 2, 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 and down 1, left 2. As many dots as possible will help you to make a nice, straight, linear function. So the lines are pretty easy. You just need to know where your starting point is and then what your slope is from there. Example 4, y equals 2 times the square root of x. Well, I just said it. Basically saying the symbol is giving away what it is, the square root function. Let's take the value of a, which in this case is 2, the value of h. Since there's no number hiding in here with the x, it must be something like x minus 0. I'll extend that out. And since x minus 0, that means that h is 0. That means that there's no shift to the right or to the left. K, I don't see any number hiding over here with the y. I don't see any other number hiding over here. So k, for the same reason as h, must be a 0. So therefore, my starting point is actually the original starting point, 0, 0, the origin. So it's still going to be the square root function starting right here. The only thing that's going to be different this time is that a is 2. What that means is I'm going to multiply my outputs by 2. So what I'm going to do first is, let's say that a is not 2. Let's say it's the normal 1. Let's graph our normal square root function. So 0, 0 is our first point. When I input a 1 into the square root function, the square root of 1 would be a 1. Now I'm just going to do a quick open circle just so you can visualize it. I'm not going to input a 2. I'm not going to input a 3. I'm going to go to the 4 next, because square root of 4 is the next perfect square. That's when I get to go up to a 2. I'm not going to do a 5 or a 6 or a 7 or an 8. I'm going to count 9 units over. I'm going to input a 9 because the square root of 9 is my next perfect square. Square root of 9 is a 3. So these are my normal points for the normal square root parent function, and I would connect those dots. But that's not what's happening here. What I'm doing here is my normal outputs were 1 and 2 and 3. That's what these orange circles are, 1 and 2 and 3 units up. What I'm going to do now is I'm going to multiply by 2 and get my new outputs. So that's why I'm multiplying by 2, because a is 2. So when I multiply 1 by 2, of course, I get 2. When I multiply 2 by 2, I get 4. And when I multiply 3 by 2, I get 6. So what happens here is I'm still going to be inputting a 1 and inputting a 4 and inputting a 9, because those are the perfect squares. But in this case, I'm going to be going up 2, 4, and 6. So when I input a 1, I don't go up 1 like normal. I go up twice as much. When I input a 4, I don't go up 2, I go up twice as much to the 4. When I input a 9, I don't go up 3 like normal, I go up twice as much to a 6. And you can see that when a is 2, we've stretched our graph to be taller than what it normally would be. So some people will like to put in the open circles where the outputs would normally be and then double them in this case. If a is 2, then we just double how far up we go and then connect our new dots. So a is a little bit trickier, and hopefully that helps you. So that's the square root function. We have our last two here. Let's look at example 5. Example 5 is a quadratic. I see a quantity squared. So let's first practice writing the word quadratic, since identifying these graphs is important to know. And let's do this. So a is the value of, we got this a, -1/2. And our value of h, which is hiding in here with the x, which is a value of +2. And our value of k, which is +5. So our new starting point, our HK, is the point 2, 5. So that will shift me 2 units to the right and 1, 2, 3, 4, 5 units up. I'm going to put my star right there. Tell everybody that that's where my starting point will be. And now I need to know what my quadratic pattern is. Well, normally our quadratic pattern, of course, would be making a quadratic graph that goes upward. I know that my a is a negative, and negative will make my graph open downward. So it's actually going to be opening downward like this. The 1/2 is also going to do something. It's going to multiply the outputs by 1/2. So ultimately, let me come down here, I am going to be multiplying my outputs by -1/2. And I personally like to deal with that in two separate things. Again, the negative just means that I'm going to be going downward, and then I'll do everything by 1/2. I'm going to do the same technique that I did last example. So my parabola, my quadratic, normally when I go over 1, I go up 1. But because of the negative, I'm going to go down 1. And then normally when I go over 2, instead of going up 4, I'm going to go down 4. 1, 2, 3, 4. Because we're squaring, remember. And then when I go over 3, 1, 2, 3 from my star, I'm going to go down 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Down because of the negative. And a quadratic is exactly symmetrical on the other side. So if I've done that here, then I'm on the left side, I'm there, and on the left side over here, and on the left side, I'm over here. So I've got my nice, what would have been my upside down quadratic if a were negative 1. But because a is negative 1/2, I don't get to go down 1 unit and down 4 units and down 9 units. I have to cut all of those in half. So when I go over 1 to the right, I don't go down 1, I go down half as much. And when I go over 2 to the right, I don't go down 4, I go down half as much. And when I go over 3 to the right, I'm not going to go all the way to 9. Half of 9 is 4.5. So I'm going to go down 4.5. 1, 2, 3, 4.5. And I'm going to do the same exact thing on the other side. There's negative a half, and here's negative 2 down from where my star was, and then negative 4.5. 1, 2, 3, 4.5. I still feel like I have so much graphing space that I could maybe do some more. Now remember, this orange dot was because I would have gone down 9, but I only went down half as much. What if I went over 4? 1, 2, 3, 4. Normally I'd go down 16. Obviously that would go off the graph patch, but in this case I don't go down 16, I go down 8. Half of 16. 1, 2, 3, 4, 5, 6, 7, 8. Let's see if I can do one more, or let me put this over here as well, because it's exactly symmetrical here. If I went over 5, 1, 2, 3, 4, 5, usually we don't ever do that because 25 is what 5 squared is, and 25 is too far off the graph patch, but half of that is only 12.5. So maybe I could do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.5. It just fits. And I can do the other one right over here. I want you to do as many points that will fit on our graph patch as possible. And I'm going to connect them all with a nice curve through all of these nice dots and put arrowheads. So that's pretty cool. I know we need some practice with the value of a, but I like this technique of doing your little open circles. If you like that, then go ahead and do that. And our final one, here's absolute value bars, so there you go. It's absolute value. A is the value of 2. It's the thing that's multiplied to our symbol. H is hiding in here with the x, and it's negative 1. And K is the number hiding over here with the y in this case, and it's positive 3. So in this case, HK is negative 1, 3. So that's a shift of left 1 and 3 up, and that's my starting point. Shifting left and up basically deals with the h and the k. Now we only have to deal with this value of 2. Since absolute value is a linear type graph, at least linear on each side, I know it's going to make a V. Since it's linear, we can sort of think of this a value as m, as a slope. This doesn't work with all 6 of the functions. It only works with absolute value, and it, of course, works with linear. So if a is 2, I can sort of think of that as a slope, at least on the right side. So from my starting point, my slope of 2 would bring me up 2 and right 1, up 2 and right 1, up 2 and right 1. Now, of course, I'm not going to continue this down here because it's not linear. Absolute value is exactly symmetrical on the other side. So if I'm going to go up 2 and right 1, the other point on the left side would be up 2 and left 1, up 2 and left 1, up 2 and left 1. And there's my absolute value. Because it's exactly linear, oops, that's kind of a bent line there. Because it's exactly linear on each side, I can treat A like a slope. If you want to do it in terms of the multiplying your outputs, remember your normal absolute value would be exactly up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1, like exactly like that. Well, if we doubled that each time, you can see that we'd be getting to these blue dots. So there's our absolute value. I like to treat it as a slope. I think it's a little bit easier. My final question actually refers back to example 5, so example 5b, just so we can practice domain and range and end behavior. This is where we'll end. Here's our nice red quadratic function. The domain of that, since this arrow is pointing all the way to the left and this arrow is pointing all the way to the right, then our domain is the set of all reals. So I can write that as the set of all reals. That's one way. Or I could write it as negative infinity to positive infinity. My range, I need to see what my lowest point is, and either one of these arrowheads is pointing all the way down. So my range is negative infinity is where I'm starting, and I'm going to go as high up as the star, which is 1, 2, 3, 4, 5 units up. So I'm going to go all the way up to that 5, and I do get to include it. I like interval notation. If you want to do set notation, that's absolutely fine. All y such that y is less than or equal to 5. Less than or equal because the graph is below our highest point. And then end behavior, remember we described the left side as x approaches negative infinity, and we described the right side as x approaches positive infinity. So let's see what's happening on the far left side. The far left side of our graph, y is pointing down. Y pointing down means y approaches negative infinity. And the same thing on the right side, we're also pointing down. So both of these end behaviors would be y approaching negative infinity. So that's great. We looked at 6 good examples of graphing by transformations, and we'll practice this in class. I'll see you then. Thanks for watching. Bye-bye.